How'd you go? Did you create some functions to prepare our EfficientNet B0 and EfficientNet B2 feature extractors? I hope you gave it a shot, but if not, let's do it together and we'll compare code, hey? Create feature extractor models. So we've prepared our data for our experiments. We've got two data sets, 10% data loader and the 20% data loader. Now, what we want to do for our feature extractor models is we want two functions. So one is going to be create a torch vision.models.efficientnet B0 feature extractor with a frozen backbone / base layers and a custom classifier head. And two is going to be basically the same thing as number one, except we're going to use EfficientNet B2. So that's the only difference. So we'd like to freeze the base layers just as we've done before by setting their requires grad parameter to false. And the custom classifier head is because these models have been pre-trained on ImageNet, they have 1,000 output classes, whereas we only want 3. Now, that will depend on how many classes you have, but in our case, we have 3, so we're changing the output classifier head to have 3 output classes. So we've seen how to do this with EfficientNet B0. Let's have a look at how we might do it with EfficientNet B2 just for some practice. So let's go import torch vision, and I'm going to create, actually, I just want to put a note here that whenever from now on, if I refer to this number 1 model, it's FNet B0, and this number 2 model is FNet B2, just for short. So I'm not saying this whole long sentence every single time. So FNet B0 is this, FNet B2 is this. So create an FNet B2. So we want FNet B2 weights. I just had to retype it out. You know when you think about something too much and you can't do it? That's exactly what just happened to me. So this is going to be our model from Torch Vision, FNet B2 weights, or our weights per se. The pre-trained weights, we want the default weights. So default recall equals best available. And just to highlight, I'm not pulling this from thin air. This is Torch Vision. This is the documentation. And we go to the unstable version for now because we want at least 0.13 plus. Just keep that in mind. That's the version of Torch Vision I'm using. So classification, we find EfficientNet B0 or B2. There we go. So if we want the weights, we can go EfficientNet B2 weights.default is equivalent to using this one. So, and there's the number of parameters we have there. There's some information about our model. So this is what we're doing. We're downloading those weights. And then if we want to set up the model, let's go FNet B2 equals torchvision.models.EfficientNet B2. The weights is going to be equal to FNet B2 weights, which is just that value we got above here. And then if we had a look at this FNet B2, what happens? So it's downloading from PyTorch. Beautiful. Look at that. Look at all those layers there. That's the power of transfer learning, is we get all of these layers in a couple of lines of code. And these are all pre-trained, by the way, because we've set the weights. So if we look at the structure of it, it's quite similar to what we've already seen with EfficientNet B0. So usually if you find a series of models with the same name, so if we jump back into here, we find all of these, ConvNext, DenseNet, MobileNet, RegNet, ShuffleNet, VGG. We've seen VGG before. VIT, so Vision Transformer. If you find the same models or a similar naming scheme such as VIT-B, that's base 16 weights, usually if they have the same naming scheme and then the number goes up, that means it's just the same style of architecture, so the same style of layers, but they've just been scaled up. So they might have more layers or more parameters or more hidden units or something like that. And that's the case generally for most of these. It's definitely the case for EfficientNet B0 to B2. B2 you can just think of as a scaled up B0. So let's jump back into here. We've got features. That's going to extract features from our images. What are the features? Well, it really depends on what the model has learned. Hopefully they are useful. It looks like they are because this model gets pretty good results on ImageNet. Then if we scroll all the way down, look how many layers there are. What do we have? We have an average pool layer that's going to turn the features tensor into a feature vector, so a vector representation of our input data. Then we have a classifier head here, which is slightly different to what we've seen with EfficientNet B0. So you'll notice that there's more in features here. That's because EfficientNet B2 is a scaled up version. So there's about 200 or so more values here. Well, actually, EfficientNet B0 was 1280. There's 130 or so more in features to this final layer. And the dropout's a little bit higher to prevent overfitting. So what do we have to do in order to turn this into a feature extractor model? Well, we have to freeze all of the base layers and we have to update the classifier head. And if we wanted to get a summary of this, let's see how we got a summary before. Model equals. I'm just going to copy this, bring that down here. Let's check out a summary of our EfficientNet B0 or B2, sorry. I'm getting all of these mixed up. Excuse me. Okay, summary. EfficientNet B2, there we go. Okay, so we've seen this before. There's our EfficientNet. We've got all the layers are trainable. This time, because we're using B2, we have more total parameters. And we have a bigger classifier feature vector here. 1408 instead of 1280. So this is something to keep in mind when you're exploring new models. You have to make sure the input and output shapes line up for every layer, including the last layer. Otherwise, you'll get shape issues. So now let's create some functions to turn not only EfficientNet B2 into a feature extractor, but reproduce what we did for EfficientNet B0. So if we do requires grad, we want to functionize this. So how about we give that a try? We'll come down here and we'll create two functions. That way, for every experiment, we instantiate a new instance of a model. Now, what could we call these? We'll go import torch vision, and we'll go from torch, import NN. And we want, I'm just going to write a note here. We've already got a note above, actually. I might just save us some space by commenting out this. Want two functions. Let's create these. So they're both going to have the same number of out features because we have how many classes? Well, we have 3, right? So let's create an FNet B0 feature extractor. We want def create FNet B0. Now we've done these steps before. All we're doing is turning it into a function this time. So we're going to go get the weights and set up a model. We want the weights is equal to torchvision.models. It's a little confusing here that one of them uses capitals and spaces, whereas the other one doesn't. But that's all right. We want weights.default. So they're the best currently available weights. Then the model is going to be torchvision.models EfficientNet B0. And we can instantiate this with weights equals weights. In a previous version of Torch Vision, you might see pre-trained equals true, but we're using the latest, most up-to-date version of the Torch Vision API, so weights equals weights. Now we want to freeze the base model layers. How do we do this? Well, we've done this before. So for param in model.parameters, we want to set the param requires grad. So this means PyTorch is no longer going to track the gradients of, we want to set this in features.parameters, not every layer, so just the features. And then we can go change the classifier head. So what was our EfficientNet B0 classifier head? Well, first things first, we're going to set the seeds so that when we set the classifier here, model.classifier, we will go model.classifier equals nn.sequential. I'm trying to remember these all off the top of my head. Sequential. But that's good practice, you know, when you try to remember these things. You don't always have to do it because that's the nature of programming, is being able to reference the documentation. But when you've got some practice, you can just start to fly through things. So in features was 1280 and out features is going to be out features 3. And I believe this was in place in their architecture. So we might also send this to the target device. Why not? And this to the target device as well for device agnostic code. And then finally, let's give the model a name so we can track the model that we're using in our experiments if we wanted to. Model.name equals fnetb0 and print. We'll just give a little info statement to finish off here. Info is going to be created new model.name model. And then we're going to return the model. Beautiful. Oh, what do we get wrong here? Didn't finish off the print. Okay, so let's call created model test. Let's see if this works. Create fnetb0. Wonderful. And then let's get a summary of it. We'll copy the summary code down here. We're going to do the same thing for fnetb2 in a second. Let's just put in created model test here. See what happens. Wonderful. That's looking like a feature extractor model that we're after. Base layers frozen, output layer trainable, total parameters. So this is 4 million or so. This is our B0 version. We have just under 4,000 trainable parameters. So we've seen this type of model before. Now let's reproduce this function, but for EfficientNet B2. In fact, we could actually probably condense this into one function and update this based on a parameter, but let's just, for now, we'll just use it as 2 functions. If you want to extend this, you can do it by one function and then just put the logic in the function to create a certain model. So we're just going to change this to B2 now. So weights, B2, EfficientNet B2 feature extractor, model is torchvision.models EfficientNet B2. We're going to freeze all the base layers. This will stay the same. This is going to be different. So let's go fnetb2.classifier. So this is when we need to update this. We want 0.3 and the in features. Remember, one of the most important things in machine learning is making sure your shapes match up. So if we didn't change this, we would get a shape error. Or actually, I wonder if we do try that. Let's see what happens. Model name, fnetb2, return the model, and then let's just change this. Created model test is now going to be fnetb2. Created that. Now, if we pass through this image size, what's going to happen? There we go. Failed to run torch info. So it's run a whole bunch of different layers, but we've got an issue here. There we go. 1408 and 1280 can't be multiplied. So we've got a shape error. But as soon as we change 1280 to 1408, let's see what happens. Oh, that's too big. Run that, run that, run that. There we go. That looks like a feature extractor EfficientNet B2 model. So it's false, false, false. And then we have nearly 7.8 total parameters. And 4,000 are trainable. So let's just we'll copy this. Created model, test, fnetb2, just to make sure both of our functions are working. We've already seen fnetb0, but we'll do it again for the hell of it. I love practicing and seeing our different model outputs. So we should get 2 different models here. Wonderful. So we'll change this one to fnetb2, and we'll change this one to fnetb0. So our fnetb2 model has 7.7 million parameters total, and about 4,000 or just over of them are trainable, whereas our fnetb0 model has, if we go down, 4 million, whereas just under 4,000 of them are trainable. So you see here now, we've got 2 models, where FNet B2 is about, thereabouts, double the size in terms of number of trained parameters as FNet B0. So I think we've got all of the pieces of the puzzle ready to go to start running our different modeling experiments. If we come back, we've got the two data sets, 10% training data, 20% training data. We've got the two model architectures that we can use, feature extractor models, B0 and B2. Now we just have to set up the number of epochs, but this is quite easy because this is a parameter to our train function, which we've used before. So let's now in the next video create some experiments and set up the training code to run all of these experiments at once and track their results so we can view them later with TensorBoard. You might want to give this a shot yourself. We've got all the tools to do so. Try it out and we'll do it together in the next video.